Hi, good afternoon, everyone. So I'm Shankar Balachandran, and I am at Intel. I work for what is called the Process Architecture Research Lab. So it's Bangalore based. So we're a group of 20 people working out of Bangalore. Uh, Before this, I was a faculty member at IIT Madras, and I switched over to the dark side. I started wearing dark T-shirts since then. So the Process Architecture Research Lab is a 7-year-old lab. Before this nomenclature of Process Architecture Research Lab, we used to be called the Microarchitecture Research Lab. We were both in the US and in India, and the MRL side of the US wound down, and we became complete owners for all the research problems related to architecture in general and microarchitecture in particular. So our focus is on problems that are relevant to both academia and industry. So we have a lot of deep collaborations. I'll talk about that a little bit later. But the problems that we look at are relevant to both Intel and industry in general, as well as to academics. So currently, our research focus is on a few different areas that I've listed on the left. So core microarchitecture and architecture are our bread and butter. So if I tell you Intel, that's probably what you'll think of, right? The processors that Intel makes. So our processors are in data centers, laptops, base stations that are there for wireless processing and so on, right? So it's a wide spectrum of processing that Intel processors are on. And some of the problems that we look at. So Intel is a big organization. It's an ocean, right? So the Process Architecture Research Lab is 20 people. So what do we really do? We work on what are called the H2P problems, right? The hard to predict problems. A lot of the work in processors, right, is speculative in nature. So you have a processor that runs in sequence. Functionally, it has to do whatever the programmer asked it to do, right? You cannot violate that. But there is a lot of speculation that happens internally. So you might have heard of branch predictors. Caching, for example, is also something which gives the same functionality without being exposed to the external world and so on. Right? There are lots of features which are inside a core which gives you the performance that you need. And the H2P problems are hard to predict problems. So, for example, in caching, what kind of data patterns should I prefetch? Right? Or in branch prediction, what kind of branch directions should I take and so on. So these are really hard problems. So when I say hard, right? So I was talking to somebody in the morning also about this. So branch prediction was at 99% accuracy even 20 years ago, right? And it moved to 99.5% a long time ago, right? There is still this 0.5% of branches that we cannot predict. And so someone may ask, what is the big deal in going from 99 to 99.5% accuracy? It's a 0.5% accuracy increase. But I look at it as it's a half the reduction in errors. And with errors, the penalties that are attached to these errors are humongous. So that's why some of these problems are really interesting. So we don't want to waste any cycle that is in the processor on work that will be thrown away later. Because a lot of the work is speculative in nature, right? You have to optimize for performance, you have to optimize for energy, right? So all of that. So that's the H2 problems that I was talking about. So there is a subgroup that looks at AI and ML. So they look at all the way from math to silicon to compilers all the way up, and they do hardware software co-optimization. So they look at algorithms, they build chips, they put them as accelerators next to cores and whatnot, and the whole shebang. There is also a subgroup that looks at system software and OS for data centers and cloud. These workloads are very different. So their data footprint and even code footprint are very, very large compared to other programs. And memory management is a big problem. So Intel doesn't want to give dollars. Okay, I will not represent Intel. Generally, industry does not want to give away dollars to other companies in the same industry, right? So memory is one piece of the cost, and cores are another piece of the cost for any data center, right? So anything that saves memory cost, right, from the computational side itself is pretty interesting to look at, right? So can we do things in the compute side and reduce the requirements for DRAM that you have in your data centers? So that's an interesting problem, and it's a very hard research problem. There's of course a lot of dollars that are there, but without the dollars also, right, as a research problem, these are very interesting. So these are the kind of problems that we look at. We have very deep collaborations with academia, both in India, in Europe, and in the US. We fund universities. I think in the last 5 years, we have funded maybe 20 different universities across the US, Europe, and India. Multiple, maybe tens of millions of dollars in the last 5 years or 6 years. We publish heavily at top places. If you're in the systems area, you probably recognize ISCA, Micro, and HPCA. If you're in the VLSI design kind of space, DATE and DAC probably rings a bell. So we also publish at CVPR and so on. Being an industry lab, of course, patenting is also something that we do regularly. So in the last 5 years, I think we have had 60 plus patents across these areas, right? So I want to talk a little bit about research philosophy that we have. So the first thing is the academic pyramid, right? So I was in academia. So generally it is about, oh, I want all my research and papers. It's the bottom, right? That's your base. And then you have patents, maybe, right? Some universities care for it. Most of us don't care as academics. Sometimes you go and build companies and you build products and whatnot, right? So the pyramid is narrow at the top, or probably non-existent at the top, right? For many academics. So when I was a faculty member, I had my publications, I had some products and patents, right? And some companies with which I worked and so on. But the top was really narrow. So when I say invert the academic period, right? Pyramid, what I meant is, so we look at what impact can we do to products, and which can bring performance, area, power, all of these things that are important for processors, right? So that's the truly important thing for us. And in the process, we get our papers and patents. So papers and patents are important, but it's not the thing that we go after. So what that means is our research is not blue sky research, right? We are very fairly grounded on practical problems that the industry faces in terms of what manufacturing we can do, in terms of what power delivery can the customers take, right? All of these things, right, dictate what kind of research we do. And the problems are then very meaningful and very interesting research problems. Like I said, so we have many academic collaborators who are also interested in the same set of problems as we are. And we have like weekly calls with them and so on. So this is a very enriching place for any researcher. So I'm a full-time researcher there, but so I'm pitching it to a community here, which is mainly students. So we have internships, research fellowships, full-time positions open. So I have flyers that I'm carrying with me. So I would like and thank you if you can take these flyers and put them up on your notice boards and give it to your departments and so on. So I'm carrying a whole bunch of them. You will have very able mentorship. So our group is headed by Srinivas Subramani, who's an Intel Fellow. So Intel Fellows, there are 100 people all over the world, right, in the history of Intel Fellows. So one of them is in India, and he's heading the lab. There are several of us who are well published. We have got our Best Paper Awards, Test of Time Awards, and things like that. So you'll be under very able mentorship for any of these positions that you are in. So I'm going to put up a poster myself with the permission from Shekhar, and you're free to come and talk to me about this more. Thank you so much.